Hello everyone. In the last lecture we discussed about applications where we need dynamic behavior of materials knowledge, and we also discussed about the structure of the course dynamic behavior of materials. So here in the structure of the course we have the stress waves. So we will first start with the stress waves. So today we will discuss some fundamentals of waves. Wave, the basic of the waves, I am sure all of you have learned in your school days. So basically if we talk about a ocean wave, let's say this is ocean bed and this is the shore. So we call wave is like this, that is on that is created in a medium that is water. So this is ocean wave. So this is the first picture come to our mind when we talk about wave. But there are different types of waves. We know light is also a wave, we know sound is also a wave. So there are different types of wave. We will talk about those waves. So waves basically transfer energy but not matter. It can transfer energy or motion without the transfer of matter. So as you know, in this case the wave transfers energy without long displacement of this much displacement of these water particles. So like any other energy transfer processes, this wave transfer, the wave that is energy transfer needs one energy source, number 2 an energy receiver, and number 3 a medium to through which the energy will be transferred. But sometimes we know that some waves can go without medium as well, even empty spaces, that is you can call vacuum, vacuum, or I can write vacuum. So for example, if we throw a stone in a small pond, let's say we have a small pond, I am drawing a top view of the pond. If you throw a stone, as we know that wave will be generated and it will travel like this, it will travel like this. So here the stone is the energy source. Energy receiver, we can assume that the bank of the pond, this is the pond, small pond, and we are throwing a stone here, stone. So the bank of the pond is the energy receiver and the medium is water, medium is water. So if we talk about different types of waves, we know whatever we discussed is water wave, then there can be sound wave or ultrasound wave, then we know about the earthquake wave. So water waves are also can be called, so big water waves are, we can call it as tsunami, which is produced from earthquakes. And then other kind of waves are visible light, radio wave, microwave, infrared wave, X-rays, gamma rays, ultraviolet rays. So these group of waves we call them mechanical waves. Mechanical waves. So this is also sometimes known as stress waves, because the resulting waves in the medium are due to mechanical stress effects. This can be called as stress waves as well, and these waves are called as electromagnetic waves. For electromagnetic waves, they were created by vibrating electric charges. So before going to details about the mechanical wave and electromagnetic wave, we will now discuss about another classification of waves, which is transverse wave and longitudinal wave. So the direction of movement of the medium is not always towards the direction of the energy transfer. So a wave in which the medium movement is perpendicular the movement of the energy transfer is called transverse wave. So for example, as we talked about a wave like this, the energy transfer is in this direction, energy transfer direction, and this is like we are talking, let's say, about a water wave, whatever we showed in the last slide. So the water particles, the medium movement is in the vertical direction. The water particle will vibrates in direction. So this is medium vibrates in a perpendicular direction to the energy transfer. So on the other hand, the wave in which medium vibrates along, or you can say parallel to the energy transfer direction. For example, sound wave, this is the earlier one was water wave at surface of the water. Okay, this is the example. Here we will talk about sound wave. So whenever some source is, this is the sound source is emitting sound. So suppose we are talking about a medium air particle will be compressed. Let's say this part air particle will be compressed, and then again the density will be less. Okay. Then again it will be compressed again. density will be high, and again here density will be low. Let's say density will be high here, high here. So this is called rarefaction, R-A-R-E, rarefaction, and these are called compression. Here this is the direction of energy transfer, and the air molecules vibrates in this direction, air vibration. That is the medium vibration is parallel to the energy transfer direction. So later we will show with will demonstrate these transverse and longitudinal wave with the help of a spring that we will discuss soon. Okay, so let us discuss this. Let us discuss about different mechanical waves and electromechanical waves. In this slide, so we will discuss about different mechanical wave spectrum and electromagnetic wave spectrum. So we have frequency in hertz and approximate wavelength in meters. So you can see that the range of frequencies and wavelength for mechanical wave spectrum and electromagnetic wave spectrum is very different. So if you see the mechanical wave spectrum, so vibration of atoms in solids has a very high frequency. It's around 10 to the power 13 hertz, and then we have medical diagnosis, which has also high frequency, and then sonic cleaning, and then we have a audible sound range. We know that from 20 to 20,000 hertz, this is the audible range, audible sound range, and in this range we have the human speech. It's a very narrow range, probably in this region. So that is human speech. And then the low frequency waves, mechanical waves, are earthquake waves, and then ocean waves, and also these tides, which are bigger ocean waves. So similarly, for electromagnetic wave spectrum, we have very high frequency waves like gamma rays, then X rays, then ultraviolet rays, infrared, then comes the microwaves. Short radio waves has this range. In this range we have FM and TV, and then lower frequencies are AM radio, and then this is actually a long radio wave range. So let us discuss how these waves travels. The mechanical waves can travel through solid, liquid and gases. It generally it doesn't go through vacuum, but electromagnetic waves created by vibrating electric charges, created by vibrating electric charges. So that can be electron, or that can be atoms or molecules which has a net electric charge. So it can be either electron or atom or molecule with a net electric charge. So, one electric charge can affect another electric charge at a distance even when there is no matter in between. That is why the electromagnetic waves can travel through vacuum. It can travel through vacuum as well. So, I will write electromagnetic wave EM. Electromagnetic wave can travel through vacuum. Like you know that sunlight comes travels through millions of kilometers to reach earth. So, that is millions of kilometers of vacuum it crosses, and in vacuum electromagnetic waves have a speed of 3 into 10 to the power 8 meter per second. In other medium this wave velocity will be different. So, if you see the nature of the waves, whether it is transverse or longitudinal, the mechanical wave, sound and ultrasound, they are longitudinal, and earthquake waves can be both longitudinal and transverse. Then water waves are generally transverse at surface and longitudinal inside. So, we will talk about amplitude, wavelength and frequency. So, let us demonstrate a simple wave propagation. Here I have a string. So, if I want to produce a transverse wave, I need to vibrate, but my left hand is fixed, and then with my right hand I am trying to produce some vibration. So, this is kind of transverse wave. So, how much I am my right hand going up and down will give us the amount of, basically the measure of amplitude, and how fast I am going up and down, that will give us the frequency, or in other way it will give us the wavelength. And so, we will see this. So, basically to describe the differences among waves, we have these parameters: amplitude, wavelength or frequency. So, if we vary the distance, so this is, let us say we have the string here and we are vibrating like this. Okay, we are vibrating like this, and the amplitude is the maximum distance the parts of a medium move from their natural position. So, this is our amplitude. Let us write it as A. Amplitude is A. So, varying the rate of vibration, if we change the rate, if we vibrate faster or slower, that will give us the frequency F. If you are vibrating faster, then frequency is higher. If we are vibrating with less speed, then our frequency is lower. Then the wavelength, the lambda, is the distance between which will the distance between one complete cycle of this. So, one complete cycle means when the string will complete one cycle. That means when you are vibrating from this point to you are vibrating from this point to this position, and then you are going back, then this position, and then again coming back to the original position. That will give you one complete periodic motion, and that distance we call as a lambda. So we have another parameter which is called time period. Time period tau, which is the time required to travel, time required for the wave to travel a distance lambda. So the time required to distance this this distance, that is lambda, we call it the time period tau, and the wave speed capital V is equal to f multiplied by lambda. That is actually the total distance divided by the time required to travel that distance. The frequency is the number of complete cycles the frequency can be defined as number of complete cycles divided by time interval so in this case let us say from x equal to 0 to this portion. So we have two number of cycles, two complete cycles. So if this waves, assume that this waves travels 100 cycles in, let us say 4 seconds, then the frequency of the wave will be 100 divided by 4, it will be 25 per second, and we write it as 25 hertz, or hertz can be written as Hz in short. So as I already mentioned that wave speed capital V is equal to wavelength lambda into frequency f. So now let us discuss about this. So we hear sound of thunder. So sound of thunder much after we hear lightning, we see lightning. So first we see the lightning, and after some time we hear the sound of thunder. That's because the wave speed V for light is much faster than V for sound. Now let us imagine there is some music function going on a few hundred meters away, and there are different types of musical instrument. Let us say you have guitar, you have tabla, or you have piano. They are all instrument playing together. So basically you will get the sound of all the instrument at the same time, because sound speed, the wave speed in air is same for all the instruments. However, these musical instrument, let us say musical instrument, I will say M1, that is let us say guitar, and then M2 and M3, they will have different frequencies. Even for guitar you have different strings and the frequencies are different, and even for other instrument the frequencies will be different. So frequencies F1, F2 and F3 will be different. That is why your wavelength should be different. So that means your wavelength should be, the wavelength for this frequency is lambda 1, lambda 2 and lambda 3. So ultimately, so you should get your frequency of the first instrument multiplied by the wavelength of the first instrument will be equal to the other instrument F2 lambda 2, F3, that means F subscript 3 lambda subs 3, that should be equal, because we know that sound speed in air is around 330 meter per second. And here we are demonstrating with the help of a transverse wave. We know that sound is a basically a longitudinal wave, but here in this case what we are showing is that black wave, that is we showing with the black line. It has a large lambda. Actually this is lambda. There are only 2 cycles that is completed till point A, and in the red one, so this lambda is smaller. Let's assume that both the waves we call it W1 and W2, both the waves reach that point A at the same time. Let's say t equal to t prime. So at the same time both the waves reach that point A. That here we can see that the lambda for W1 is lambda 1. Let's say we assume it is a lambda 1, and here W2 lambda is for W2 it is wavelength is lambda 2. That means lambda 2 is, here we will write here, lambda 2 is bigger than lambda 1, but as both the waves reach that point A at the same time, that means our velocity are equal, V2 equal to V1, and that means our frequencies are different. So frequencies are different, that is the frequency of wave 2 will be less than the frequency of the first wave. So let us discuss about the vibrating string. Now we will do some derivation to obtain the wave equation. This is the string and we have x and y coordinate here. At time t equal to 0 we are representing the wave with a solid line, and then time t is not equal to 0, that means after some time the wave reach here, that is shown by dotted line. So this is the simplest, the vibrating string example is the simplest case of wave propagation. That is the most simple case, wave propagation. So basically the shape of the wave is, we are taking the simplest one, the sinusoidal wave. As you can see, the y equal to 0, we are talking about now t equal to 0, the wave position at t equal to 0, y equal to 0 at these positions, y equal to 0, y equal to 0, y equal to 0. That means y equal to 0 at x equal to 0 or x equal to lambda by 2, that we already know. Lambda means the wavelength, which is lambda or 3 lambda by 2. Similarly we can go on. So we are talking about this condition at time t equal to 0. So the amplitude is y naught and wavelength is lambda, we already told that. And actually if we it is understood that we are vibrating this end, and that is why at time t is not equal to 0, that means at, let us say, after some second, it is not actually second, it may be after some, let us say, millisecond, we got this dashed line. So we will now see the wave speed expression, wave speed v, capital V, will be equal to the total distance travel x divided by total time of wave travel, which will be equal to lambda by tau. As we discussed in a previous slide, that tau is the time required to travel one wavelength, that is lambda. So that is why we can express V is equal to lambda by tau, and this 1 by tau is nothing but the frequency, because tau is the time required to travel one wavelength. So 1 by tau is equal to frequency. So that is why we can write as lambda by f, V equal to lambda multiplied by small f is the frequency. So as we said that this is sinusoidal wave, so it can be expressed as y equal to y naught, which is the amplitude, multiplied by sine of twice pi x divided by lambda. So that is basically, you can see from here, even we mentioned it earlier also, if x equal to 0, let us say what happens, x equal to 0, the entire this expression will be 0. If x equal to lambda by 2 at this point, lambda by 2, this term will be sine twice pi lambda by 2 by lambda. So that means sine pi, which is 0. And then similarly if you talk about x equal to lambda, then again it will be, y will be 0. Similarly x equal to 3 lambda by 2, x equal to 3 lambda by 2 here, and here x equal to lambda, in this case x equal to lambda by 2. So sorry, 3 lambda by 2. So in these, at these positions the y will be equal to 0. So that is why we can represent the shape of the wave, with these expression. Similarly we can also have y equal to y naught sine twice pi ft. That is another way to express it, because we can check that if we multiply, suppose at different time intervals, so we will get that this expression will give you the values pi, twice pi, 3 pi, and so on. So this will be again, so y will be 0 at those positions. So in the previous slide we have derived these equations, y equal to y sine twice pi x divided by lambda, y equal to y naught sine twice pi ft, frequency and time, and this is these two equations, different version of the same one equation of harmonic vibration of the source. That means in this case I was in the case of string I was my hand was at the source hand. So I was vibrating like this, my hand was the source. So the equation of the source, that means at t equal to 0 we have this equation, but if you want to know equation at any x and t, so we need to, that means when t is not equal to 0 we need to consider a time lag. So how we represent this equation? It is written as y equal to y naught sine twice by f t, which is we found it here. Now what we will do is, for the time lag we can write it like this. So this is the equation for at any time x and t. So the time lag is like this. So at y equal to 0, earlier at the source, let us say after time t prime, this, let us say this is an x actually. So this is, let us say x prime, and let us say it takes time t prime, which is x prime by v. Okay, let us assume this is distance x, and let us assume it takes time t prime to cover this distance. So x by v is the time. So that means that time lag t from t, we subtract the t prime, so that we know now this is a new position of this wave. So why we are subtracting this minus sign? Because the wave is traveling towards right direction. So it is traveling towards this direction, that is why this negative sign comes. So now this equation will give the displacement at any time x, at any time t and any position x. So which can be, this equation can be written in another form, this form. How we can do it? We know that v is equal to f lambda, and then if you rearrange it f by v, from here if you see, here we have f and v. So f by v will be equal to 1 lambda, and that will give you this equation. This relation will give you this equation, and this is the displacement equation of displacement at any position x and time t. So now we will take a segment from that string. Let us say we are taking a small segment out of the string. Let us say this is the small segment ds. We will take this segment and we will go to the next slide. So this entire portion is the segment ds of that string. ds, and let us say this is point A, this is B, and for our reference we are putting this as C. So, the x direction length of the segment is dx, and the y direction length we can get it as the partial of y with respect to x multiplied by dx. So, as you know, y is a multivariable function, is a function of x and t. Y is a function of x and t, both position and time. So, we can express this vertical distance from B to C as this way, and this angle of first we should understand that the string is in tension, and this is the line tension acting along the string. There are two assumptions here, that this assumptions are the string is thin and also the tension along from point A to point B will be not very different, that is tension is constant, So, then we will see that this is, there is an angle, this angle is theta A and this angle will be theta B. We should understand that this string is not exactly the straight line, because if you see from the earlier the string vibration figure, so it is like this. So, if you take a string from some this portion, this will not be exactly straight line, that is why theta and theta B will not be same. So, this will probably the theta will be something like that, and this theta B will be theta subscript A plus differential of theta. Sorry. So, now first, as this segment is in motion, so we will apply the Newton's second law. Newton's second law. Second law of motion. So, this is all the motion takes place in the y direction, we assume that, and so there will be some component of tension in this direction. So, basically the vertical forces, mass multiplied by the acceleration in y direction, which will be rho, is the line we call line density or mass per unit length, and as we know y is a function of x and t. So, that is the rho ds will give us the mass, and the acceleration is double partial of y with respect to t. So, here if we consider all the vertical forces, we see that this is t sin theta subscript b and this is t sin theta subscript a. So, the vertical forces is equal to, the resulting vertical force is equal to line tension multiplied by sin theta subscript b minus line tension multiplied by sin of theta subscript a, which is then again equal to, we can take t common out of this expression, and then sin theta a plus d theta, differential of theta, and then sin theta a. This expression will be equal to rho ds second partial of y with respect to t. So we are assuming that all the motion takes place in the y direction. So there is another assumption that all motion in y direction. Why all the motion in y direction? Because we are giving only y direction motion of the string. So moving on from this, so the expression what we got in the previous slide, we will multiply the previous expression and at the same time multiplying and dividing, at the same time we are dividing the expression by d theta. So we got this, and but we know that this expression sin theta a d theta minus sin theta d theta is a kind of differential of sin theta a, the expression on the top, and actually d theta. So basically it's a derivative of sin theta a with respect to theta, that will give you cosine of theta a. So from the previous expression what we got is t cosine of theta d theta is equal to rho ds second partial of y with respect to t. So this comes from this equation, and also we know that from the right angle triangle ABC, cosine of theta that is based by hypotenuse. Okay, from the right angle triangle ABC we can get that cosine of theta a will be equal to dx ds. So basically if we have the line segment ds, and so we have dx, this one is dx, so this is cos theta a. You can get an expression finally like this, ds will be equal to dx divided by cos theta a. So we will now try to eliminate theta. To eliminate theta, eliminate d theta. What we can do is, we know that tangent of theta for a right angle triangle is perpendicular by base. Here in this case, so we have x plus dx and x. This one is partial of y with respect to x and multiplied by dx. So ultimately from the tan theta a we have x plus dx minus x, that means this dx, and we have this minus this, so basically this minus this, so and finally it ends up with partial of y with respect to x, and from that we can get partial of tan theta a, partial of tan theta a with respect to x. I mean we take taking partial derivative on both the sides, and that will give you second partial of y with respect to x, and this will give you sec square theta a partial of theta with respect to x, and this will give you differential of d theta a will be equal to dx2 cos square theta a dx. So now from the earlier equation, so we got this dx ds equal to dx divided by cos theta a, and the another we got that this one. So let us say assume we call this is as a and this one is b. So from a and b and c, so from a, b and c, so what we can get is t cos theta a cos square theta a dx is equal to rho dx cos theta a second partial of y with respect to dt2, and this will give you t cos to the power 4 theta a second partial of y with respect to t equal to rho second partial of y with respect to t. So for very small oscillations, generally the oscillations, if we consider oscillations are very small, so cos theta will be equal to 1, and that will give you this equation. So this is the differential equation for wave, or you can call it wave equation, differential equation describing wave. Describing a wave, or you can call it a wave equation. So we will show some demonstration on basic aspects of wave propagation. Two of the teaching assistants, my PhD students Akshay and Bikram, will show some of this demonstration with the help of a helical spring. So we will show longitudinal and transverse wave propagation. You will see what happens when the spring has spring is tighter or it has higher stiffness. So far we have discussed about the wave speed of vibrating string, and we saw that depends on the line tension, and that means if it is line tension is higher, that wave speed is higher, and that is square root of the ratio of line tension and mass density. Similarly, so in a solid medium, the elastic wave speed is depends on the Young's modulus. So if we have a higher stiffness spring, that means if we stretch the spring, then we will see what will happen to its wave speed. So we will show the longitudinal wave, let's say actually longitudinal compression. Faster maybe. So now we will show the transverse wave. So now we will show the transverse wave. So now we will so that if we stretch the spring more, we are stretching it more, and then we can see that the wave will propagate faster. So we can see that this is a faster wave propagation than the previous case, where the spring was not stretched much in the previous case. Then we will see what will happen if we increase the frequency. So you can show two cases. First one is slower, and then you can have a higher. This will first with a lower frequency, that means slower one, okay, and then we will go to higher frequency. One more higher frequency. So in this lecture we have discussed about the basics of wave propagation, and then we also discussed about the wave equation for a vibrating string, and then in the next lectures we will discuss about the difference between quasi-static and dynamic deformation from atomic perspective, and then elastic wave and its classification. Thank you.